It's the moment we've all been waiting for. You're in Accelerated Algebra 2 and Trig. So, what are we going to start? You know it, trigonometry. Welcome to chapter 12, where we are going to talk a lot about triangles. Let's go. All right, here we go. We're talking about triangles, and so hopefully some of this is maybe review, but if not, that's okay. We're going to go over all of it. So we're dealing with triangles. So remember, a triangle is defined with 3 corners, 3 sides. And now there's some specific relationships that are true for all triangles, but we're going to start with our right triangles. So a right triangle means that we have a 90 degree, I guess I should do it up here, a 90 degree angle. That's what this little box means. And so if we label our 2 sides as A and B, doesn't matter which one is which, but as long as C is the hypotenuse, so we call these 2 just sides, and the hypotenuse is the longest side, as well as the side that is directly opposite the 90 degree angle. So now we can talk about this thing called the Pythagorean theorem. So if we take the lengths of each side, call it A, B, and then C is the hypotenuse, we have a formula or a relationship where we say A squared plus B squared equals C squared. So hopefully that triggers a little bit of memory. It's one of our more popular, like A squared plus B squared equals C squared. But it allows us to basically, if we have 2 sides of a triangle, we can always find the third. And this is very helpful in both trig and just in general, like if you're doing some building or anything that involves triangles. So let's do an example or two. We're looking at number 1, find the missing side, give your answer in simplest radicalist form. So we have A squared plus B squared equals C squared. So let's plug that in. Oh no. So we've got, if we call this my A, this my B, and this is going to be my C. So we've got 4 squared plus 8 squared equals x squared. So these 2 are just numbers. So I'm actually going to throw that into my calculator. 4 squared plus 8 squared. So that's going to be a total of 80 equals x squared. We're going to take the square root of both sides. Square root both sides. And then, so we're going to simplify this. This is, again, we want to keep everything in radical form. So you cannot plug it. You can plug it into your calculator to see if it's a perfect square, but it's not. We're going to simplify that down to x equals 4 square root of 5. So normally when we square root both sides, we do a plus or minus. How do you have a negative length? So it's kind of a trick question. So there's an implied task here. Since we are dealing with a length, a real live actual measurement, we can't have a negative number. So we just throw out that negative number because it doesn't make sense. So our number is just x equals 4 square root of 5. And we found it using A squared plus B squared equals C squared. So we're looking at number 2 for another example. So we see our 90 degree. Opposite of that, this is our hypotenuse. So the only thing that we got to make sure we get in the right place is our C squared. So our 24 is going to be our C. So we can call this A, B, C. So then we've got 22 squared plus x squared equals 24 squared. So the way I like to solve these things is I take all that stuff, turn it into numbers so that I don't have to deal with squares. So 22 squared is 484 plus x squared equals 24 squared, which is 576. So with that, it in my brain, it helps me see it a little bit better. So from here, we're just going to subtract 484 from both sides. And then we're going to have x squared equals 92. We're going to square root both sides. So then we're going to we'll simplify that square root, and we'll end up with 2 square root of 23 as our final x. So the Pythagorean theorem works for any right triangle. So again, that means that you have a right angle in there. And so the Pythagorean theorem will still work for all these other types of triangles. But we have an even more specialized version of a triangle. And again, you're going to see these over and over and over again. But they're both right triangles. But we've got a 45, 45, 90 triangle. And we've got a 30, 60, 90 triangle. So these are just referring to the degrees of our angles right here. And there's some special properties that we have with those as well. So number one, we're going to start with the 45, 45, 90 triangle. So because both of these angles are the same, both of these sides are going to be the same. And then if we were to call these sides as like 1 and 1, the hypotenuse is going to be square root of 2. So another way we can say that is if we define our side lengths as x, then our hypotenuse is going to be x times the square root of 2. So that's a really helpful relationship that you should kind of memorize. It'll help you a lot if you haven't memorized, but I'm not going to make you memorize it either way. So that means that our legs are both going to be x, and then our hypotenuse is x square root of 2. So let's try some examples out with the 45, 45, 90, and then I'll show you the other triangle. So using that pattern, that relationship, if we just go down this left side, it's not terrible. So if we're looking at number 3, I see that this side is 10, and because I know that it's a 45, 45 triangle, that means that this side is equal to that side. So I can tell you that my x is 10 right off the bat. And my y, remember my relationship was x square root of 2. So in this case, my x is 10. So my y is going to be 10 square root of 2. And that's all it takes. Just using that pattern makes our lives a lot easier. So if we're looking at number 5, we are given this guy, 14 square root of 2. And remember, so we see that it's a 45, 45 triangle. And our pattern is the two side lengths are equal. And then the other one is the side length times square root of 2. So that means that this is both going to be 14. Because you can kind of see this is x times square root of 2. So my x and my y are both going to be 14 because it's a 45, 45 triangle and those sides are the same. And we missed number 4, so here it is. I see that it's a 45, 45 triangle. It's got 16. Remember, we've got our x and y. Those sides are going to be the same. So, okay, it's not super square root of 2. Like, we don't see that initially. But that's okay. We can still figure it out. So, remember, our pattern was this here. On the hypotenuse is x square root of 2. So now we have, let's see here. How do I want to phrase this? Yeah, so we have x times square root of 2 equals 16. And we just need to figure out what that x is, and that's going to give us both of these values. So if we divide both sides by square root of 2, we have x equals 16 over square root of 2. Hopefully you remember that we don't like radicals in the denominator, so we multiply both sides by square root of 2, and we have 16 square root of 2 over 2. 16 and 2 simplify into 8 square root of 2. So our x, both of our side lengths are 8 square root of 2. Okay, so our next special triangle, that's what we call them. Again, it's a right triangle, because we have this 90-degree angle. But this time, our angles are 30 degrees and 60 degrees. So again, just like the 45-45 triangle, there's a specific pattern. And it goes x, 2x, x squared of 3. The way I remember it is I always call it 1, 2, square root of 3, because that kind of goes in order, right? 1, 2, 3. But you have to remember that there's that x there. So if this is not always 1, but it's a multiple of 1. But that's just how I remember it. 1, 2, square root of 3. So my short length, so my shorter length is going to be x. My longer length is going to be x square root of 3. And then my hypotenuse is going to be 2x. And again, I always remember 2 is bigger than square root of 3. So the hypotenuse, I always remember that it's the longest one. So this has to be your biggest number. So I remember the numbers 1, 2, square root of 3. And then I kind of have to use my brain and logic where they go. But you get very comfortable with that after a little bit of practice. So number 6, we can see that there is a 30-degree mark there. So that means that it does have to be a 30, 60, 90 triangle. We know that 60 degrees would be right there based on our pattern, and that this is already 90. So that means that our pattern is, let's see here, what? 1, 2, square root of 3, right? So our x, our shorter side is equal to half of our hypotenuse. So I'm just going to set that equation up. So we've got our x equals, no, I'm just kidding. We're going to say, we're looking at this guy right there. So 2x equals 8. The way that I got there is from that pattern, our hypotenuse is 2 times the smaller length. My smaller length is x. So I said 2x equals 8. So then from there, we can say that my x equals 4, divide both sides by 2. And then our y is going to be, 4 square root of 3, because our x is 4. So again, that's all part of that relationship. And once you kind of have that relationship ingrained, these problems become a lot easier. So looking at number 7, obviously I see a 60, so that means it's going to be a 30, 60, 90, so I can call this 30 degrees. You don't really have to write that if you don't want to, but sometimes it helps. So we need to figure out what x and y is. So my x is my hypotenuse right there. I know that because it's opposite my 90 degree. This is going to be my side. So because it's a 30, 60, 90, I always like to write 1, 2, square root of 3. So remember, that's the way I remember it, but the actual kind of formula that was given to us is, what is this? So if this is y, so then we've got y square root of 3, and then 2y for the hypotenuse. Okay, so we can do some math with that. We'll get rid of this so we don't confuse anybody. So our y is also equal to 2x. But we can start over here with our 27. That probably makes the most sense. So our 27 is equal to square root of y. So we can say 27 is equal to y square root of 3. I'm sorry, I said that wrong. I said square root of y. So then we're going to divide both sides by square root of 3. So we got y equals 27 divided by square root of 3. We're going to multiply the top and the bottom by square root of 3 over square root of 3. So then we're going to have 27 square root of 3 over 3, which equals 9 square root of 3. So our y is going to be 9 square root of 3. So then from that, we can figure out our x. It's just going to be twice that. So it's going to be 18 square root of 3. So these special triangles show up all the time. So let's get comfortable with them. So number 8, again, 30, 60, 90 triangle. This is my smaller side. So this is my 1, this is my 2, and this is my square root of 3. And so let's see here. This is our x right here. So our, pattern says that our y is going to be this number times the square root of 3. So, okay, so that means that our y is going to be equal to 5 square root of 6 times square root of 3. And you should be able to do this. So this is going to be 5 square root of 18. So we just multiplied the inside of the square roots together. And then it looks like, what is it? 4. Yeah. No, 3, 6. Something. Okay. I was trying to do it in my head. It didn't work, so here I am. Okay, so looks like a 3 does come out. So our y is going to be 15, because 3 times 5 is 15. Square root of 2 left over. So that's our y. So our y is 15 root 2. We can shorten square root to root. So then our x, this guy right here, is just twice this. So that's easy enough. So that's just going to be 10 square root of 6. And there you go. All right, what about triangles that are not special triangles? So let's say you have a triangle, you have some angle, but you don't know, or it's not one of the 30-69 triangles or the 45-45 triangle. So that is where we get into trigonometry. So we've got trig functions. You've probably seen them on the calculator, and they are called sine. That is how it's called. That is how it is abbreviated. Cosine. That is how it is abbreviated. And tangent. That is how it is abbreviated. So some vocabulary. Typically this thing right here, we use the Greek letter theta. That's what that means. That just represents an angle. We kind of reserve theta always to represent an angle. So anytime you see a theta anywhere, you should recognize that that is an angle. So we do have these trig functions, again, sine, cosine, tangent, and they represent a relationship between the angle and the sides of a triangle. So we can use these trig functions to help solve for different things in the triangle. So let's define some of these relationships. By the way, it's the same thing as like pi. So every circle has a relationship between the diameter and the circumference. Every triangle, right triangle, has a relationship between its angles and its sides. And that's where these things come from. Now, you may have heard the phrase SOHCAHTOA. So that's what we're doing. SOHCAHTOA. And that is a way to remember all of these things. So our sine is defined as opposite over hypotenuse. So that means if we look at this theta, the sine of theta is going to be the opposite over hypotenuse. So we can also write, what is that? Equals A over B. I'm sorry, A over C. My bad. So cosine is defined as adjacent over hypotenuse. So we've got cosine of angle. This is the adjacent, and this is our hypotenuse. So we've got opposite, adjacent. Our cosine is adjacent over hypotenuse. And that's right there. So in our triangle, that would be B over C. Last but not least, our tangent is so we've got our theta right here is opposite over adjacent. So that's going to be like A over B. So you will hear almost every math person out there refer to this as SOHCAHTOA. And it's just a phrase that we use to remember how these things work. So sine is opposite over adjacent. Sine opposite over hypotenuse. I'm sorry, I said that wrong. It is opposite over hypotenuse. So cosine is adjacent over hypotenuse. Right there. TOA, tangent, is opposite over adjacent. So using these functions, we can solve for things. So while we're at it, we also have the inverse of these functions, and it is just the same function, just flipped upside down. So cosecant is the inverse of sine. Secant is the inverse of cosine, and then cotangent is the inverse of tangent. I had a math teacher tell me once that each one of these groups has at least one co in it. So that's kind of how you can remember it. So sine does not have a co in it, so its opposite is cosecant. Cosine already has a co in it, its opposite is secant. Tangent doesn't have a co in it, so its opposite is cotangent. Although these are pretty obvious how they go together because they both have tangent in them. So what the cosecant, secant, and cotangent are just going to look like, 1 over sine of theta. So that would just be like hypotenuse over opposite. Secant would just be the opposite of cosine, so that would be hypotenuse over adjacent. And then cotangent would just be adjacent over opposite. Okay, let's put it all together using number 9 here. So we have a triangle with a random theta. Not random, we can figure it out. But so first of all, we are going to find all 6 trig ratios for theta shown in the triangle. So first of all, we need to know what this value is. So in order to figure that out, we're going to use from earlier in this lesson our Pythagorean theorem. So we can do 16 squared plus 30 squared. We can call this x equals x squared. We're going to turn both those into numbers. That's 256 plus 900. And that's going to equal x squared. Add those together. We have this wonderfully huge number. And then we're going to square root both sides. And if you just use your calculator to square root that, you will find that 34 equals x. So we can say x equals 34. So that's going to help us with all of our trig functions. Okay, so here is our theta. So our sine is opposite over hypotenuse. So we're just going to write 16 over 34. And then hopefully from there you should recognize that, I should probably reduce that. So that's going to equal 8 over 17. So our cosine is going to be our adjacent from our angle over our hypotenuse. So our cosine is just going to be 30 over 34. We're going to reduce that, and that's going to get down to 15 over 17. And our tangent is going to be opposite over adjacent. So that's going to be 16 over 30, which will then reduce to 8 over 15. So our cosecant, secant, and cotangent is just going to be these fractions flipped. So I'm not really going to go through those too much, but it is just going to be 17 over 8, 17 over 15, and then 15 over 8. So just as an example, if we're going to do cosecant, so that is the opposite of sine. So instead of doing opposite over hypotenuse, we're going to do hypotenuse over opposite. So that's all that is. Hello, I moved. I'm up here now. Up here now. Anyway, let's look at number 10. Given the ratio for cosine, find the remaining ratios. What should we do? I have an idea. Let's draw a picture. So we have some triangle. I like to make, so it is a right triangle. And I like to make one side bigger, one side smaller. And then there's my hypotenuse. I guess it doesn't matter. We're going to just arbitrarily define my theta as right there. So now we have our cosine defined. Remember, cosine is adjacent over hypotenuse. So if I put my theta right there, my adjacent is going to be 2. My hypotenuse is going to be 3. So how do we find that third side? If you said Pythagorean theorem, you're right. So we can call this x. We're going to have x squared plus 2 squared equals 3 squared. These are numbers that I can handle, which is great. And then we're going to move the 4 over. X squared equals 5. Yeah, I knew that. So then x is just going to be square root of 5. So my x equals, we're going to put it underneath that, square root of 5. So then from there, we can find all the rest of them, right? So sine of theta is going to be opposite square root of 5 over 3. Tangent is going to be opposite over adjacent. So that's going to be square root of 5 over 2. Secant is going to be the opposite of sine, 3 over square root of 5. Oh no, we can't have a square root in the denominator. That's okay. We will just rationalize it. No big deal. So now we have 3 square root of 5 over 5. Don't even have to simplify from there. Secant is just going to be 3 over 2. And then cotangent is 2 over square root of 5. Oh no. We'll rationalize it. That's okay. Ugh. So then we're going to have 2 square root of 5 over 5. All right, so you know that I'm not really into memorizing stuff, but if you're going to memorize something, this is a really good section to memorize. So you will see these special triangles over and over and over again, and you're going to be doing a lot of trig with them. So we can look at each one of these, and we've got a picture over here, and we have certain relationships. So let's figure those out. So if you remember, our 45-45 triangle looks like x square root of 2. I remember it as 1 square root of 2, but this is probably a better way to remember it. So then our 30, 60, 90, we've got x, let's see here, x, 2x, square root of 3x. I remember it as 2 square root of 3. But from there, you can find all of these different trig functions, right? So we've got these relationships. So sine of 45 is going to be opposite over adjacent. So we've got opposite x over x square root of 2. And then our x's cancel out. We have 1 over square root of 2. Can't do with that. So then we rationalize it. So then we've got our final answer is square root of 2 over 2. Cosine of 45. So we're looking here. Cosine is adjacent. It's actually going to be the exact same. So yeah, I'm just going to write square root of 2 over 2. And then tangent of 45, let's look at that. Opposite over adjacent. Hey look, that's x over x. That equals 1. It's convenient. Sine of 30 down here, going to be opposite over hypotenuse. So we're going to have x over 2x. X's cancel out, so that's 1/2. Cosine of 30, let's look at that. That's going to be square root of 3 over 2. Tangent of 30 is going to be opposite over adjacent. So that's going to be x over square root of 3x. X's cancel out. 1 over square root of 3 needs to be rationalized. So we're going to have square root of 3 over 3. And then sine of 60, we're looking at square root of 3x over 2x. X's cancel out. Square root of 3 over 2. Cosine of 60 is going to be x over 2x equals 1/2. So again, cosine, I'm looking here, adjacent over hypotenuse. Tangent of 60 is going to be opposite over hypotenuse. No, it's going to be opposite over adjacent. So we got square root of 3x over x, which is just square root of 3. So these are relationships that are going to pop up over and over and over again. So get used to figuring them out. There's 2 ways to kind of go about remembering these. Either you might get so comfortable that you just recognize that these things go together. I'm not there, but I do have this picture kind of memorized. Again, I view it as 1 square root of 2, and I view this one as 1, 2 square root of 3. But you got to remember that there are x's there, and they can get bigger or smaller, things like that. But welcome to Trig. Here we go. I'll see you in class.